and welcome to the Screencast on the graph of the natural logarithm. We know that the natural logarithm n of x equals the natural log of x is the inverse of the natural exponential function e of x equals e to the x. As such, properties of inverse functions are true about these two functions. For example, we've already established that the natural logarithm n of x equals the natural log of x has the set of all positive real numbers as its domain and the set of all real numbers as its range. In addition, being the inverse of e of x equals e to the x, we see that when we plot the natural logarithm and natural exponential functions on the same coordinate axes, their graphs are reflections of one another across the line y equals x. As a result, because 0, 1 is on the graph of the natural exponential function, 1, 0 is on the graph of the natural logarithm function. Indeed, for any point, a, b, that lies on the graph of e of x equals e to the x, it follows that the point b, a, lies on the graph of the inverse n of x equals the natural log of x. These observations all illustrate that inverse functions say the same thing, but from two different perspectives. We know that the graph of e of x equals e to the x is always increasing, and we see here that the graph of n of x equals the natural log of x is also always increasing. We should note that the graph of e to the x increases more and more rapidly as x increases. That is, e to the x increases at an increasing rate and is thus always concave up. Contrast that with the graph of the natural log of x. The graph of the natural log of x grows more and more slowly as x increases. Another way to say this is that the natural log of x grows at a decreasing rate. And for this reason, the natural log of x is always concave down. It should be noted that even though the natural logarithm function grows very slowly, it does grow without bound. For example, if we want the natural log of x to equal 1,000, then we can choose x equals e raised to the 1,000. Obviously, e raised to the 1,000 is a very large number, but this just illustrates that if we make x large enough, then we can make the natural log of x as large as we want. So the natural log of x does grow and grow and grow without bound. And as a result, we can use arrow notation to say that the natural log of x increases without bound as x increases without bound. While the natural exponential function and the natural logarithm and transformations of these functions are connected and have certain similar properties, it will also be important to be able to distinguish between behavior that is fundamentally exponential and fundamentally logarithmic, and soon you will gain practice in doing so.